What if everything we believe about where we are is incomplete? For most of human history, we looked up at the night sky and saw a ceiling painted with light. Ancient astronomers counted a few thousand points scattered across the darkness. Then telescopes arrived, and those points multiplied. Thousands became millions, millions became billions. Each generation peered deeper into space and discovered that the cosmos was far larger than anyone imagined. Yet even with decades of the most sophisticated instruments humanity could build, even after mapping distant galaxies and measuring the oldest light in existence, we still miscalculated. We thought we had reached the boundary of understanding that our census of cosmic architecture was nearly complete. A single instrument, positioned 1 million miles from Earth, proved us wrong in ways that challenged the foundation of cosmology itself. The observable universe does not measure what we thought it did. Light from the oldest galaxies has been traveling toward us for nearly 14 billion years, moving at the absolute speed limit of nature. Common sense suggests that these photons should have covered 14 billion light-years of distance. They have not. The galaxies that emitted this ancient radiation now sit 46 billion light-years away, separated from us by a gulf nearly 7 times wider than the age of the cosmos should permit. Space itself has been expanding while that light journeyed across the void, carrying those distant sources farther from us, even as their photons moved in our direction. The sphere we inhabit stretches 93 billion light-years in diameter, a volume so immense that previous estimates underestimated the true scale by factors we are only beginning to grasp. This revelation arrived when astronomers directed an infrared eye toward a patch of darkness slightly larger than a pinhead held at arm's length. That region appeared mostly empty in earlier surveys, a quiet zone between the bright galaxies that populated visible light images. When the new observations returned, scientists found themselves staring at nearly 800,000 galaxies hidden in what they believed was vacant space. Not dozens, not hundreds. 800,000 distinct collections of stars, each containing billions or trillions of suns, each separated from its neighbors by distances measured in millions of light-years, all compressed into a field of view that would fit comfortably behind 3 full moons. The implications ripple outward in every direction. If this density represents the average cosmic population, then the total number of galaxies inhabiting the observable universe climbs from a few hundred billion to several trillion. Every estimate of how matter organizes across space must be revised upward. Every calculation about planetary abundance, about the raw potential for complexity and chemistry, and perhaps even biology scattered throughout existence, multiplies by factors of 10 or more. We thought we lived in a universe containing 200 billion galaxies. We might inhabit one containing 20 trillion. But the shock does not end with mere numbers. Among those hundreds of thousands of newly revealed galaxies, a significant fraction formed during an era when nothing substantial should yet exist. Light from these objects departed when the cosmos was less than 500 million years old, a span representing barely 3% of the universe's total history. Standard models of structure formation predict that this epoch should host only small, dim, primitive assemblages of stars, simple systems still gathering their first generation of stellar material. Instead, observers found galaxies shining with the luminosity of billions of suns, structures stretching thousands of light-years across, stellar populations that appear far too massive and far too developed for the limited time available since the beginning. One galaxy in particular forced astronomers to question whether they misunderstood something fundamental. It appeared when the cosmos was only 290 million years old, blazing brightly enough to be detected across 13.5 billion years of expanding space. Spectroscopic analysis revealed not just hydrogen and helium, the primordial elements forged in the immediate aftermath of creation, but carbon, oxygen, nitrogen, the products of stellar fusion and supernova explosions. This meant that an entire generation of stars had already lived and died before this galaxy even formed. The timeline kept compressing backward, squeezing more cosmic evolution into less available time. Researchers described finding this object as comparable to excavating advanced technology among ancient ruins, something that exists before the conditions that create it should be possible. The problem extends beyond individual galaxies. At the hearts of some of these early systems sit black holes weighing millions or billions of times more than our sun. These gravitational monsters consume matter at ferocious rates, their accretion disks blazing with radiation that outshines entire galactic populations. Building such objects requires accumulating enormous mass through gradual feeding, a process that theoretical physics says should take billions of years. Yet there they burn in an infant cosmos, active and fully formed when the universe was less than 500 million years old. The mathematics does not permit this. The growth rates calculated from first principles cannot reach the observed masses in the time available. Something about the early universe either worked differently than current theory predicts, or the theory itself contains gaps we have not yet identified. The contradictions multiply with each new observation. Massive structures spanning tens of millions of light years appear in epochs when gravity should not have had sufficient time to pull such concentrations together. Galaxy groups that should be sparse and loosely organized instead show tight clustering and rapid star formation. The cosmic web, the largest architecture in existence, threads through space with filaments connecting supermassive nodes where thousands of galaxies congregate. Mapping this web backward in time reveals that its essential structure emerged far earlier than models anticipated. By the time the universe reached 1 billion years of age, the skeleton of dark matter had already organized into recognizable patterns, guiding ordinary matter into channels and intersections that would eventually become the large-scale structure we observe today. Dark matter itself remains invisible, interacting with ordinary material only through gravity. It comprises 85% of all matter in the cosmos, yet it emits no light, absorbs no radiation, and passes through normal atoms as if they were empty space. We detect its presence only through its gravitational influence on things we can see. Stars orbit too quickly in their galaxies. Galaxy clusters hold together despite containing insufficient visible mass. The cosmic web would not exist without dark matter, providing the scaffolding along which ordinary matter flows. For decades, scientists theorized that this invisible component must line the filaments connecting major structures, but no observation had confirmed dark matter's presence on those threads. Recent measurements using gravitational lensing finally revealed the signature, detecting dark matter distributed along the thinnest terminals of cosmic web architecture, the delicate strands connecting individual galaxies to the larger network. The universe's hidden skeleton has been mapped, confirming that structure extends far beyond what any telescope can directly photograph. Between the filaments stretch voids, enormous regions where almost nothing exists. These cosmic deserts extend for hundreds of millions of light years, containing fewer than 10% of the average matter density found elsewhere. Imagine standing in the center of such a void. Look in any direction and you would see darkness extending for tens of millions of light years before encountering the nearest galaxy. Light from the most distant structures visible from that vantage point would have been traveling toward you since long before Earth existed. The contrast between dense filaments and empty voids creates the universe's defining characteristic at the largest scales, a pattern of matter concentrated into thin threads and massive nodes, separated by immense volumes of near-total emptiness. The architecture reveals itself through light that has been transformed during its journey across space. Every photon emitted by a distant galaxy gets stretched as the universe expands. Ultraviolet light shifts into the visible spectrum. Visible light becomes infrared. Infrared extends into wavelengths far beyond what human eyes can detect. By the time radiation from the most distant galaxies arrives at our telescopes, its wavelength has increased by factors of 15 or more. Blue light from hot young stars reaches us as deep infrared radiation, invisible to instruments designed to observe the visible spectrum. This is why earlier telescopes missed so many galaxies. They were looking in the wrong part of the electromagnetic spectrum, searching for light that had already transformed into wavelengths their detectors could not capture. The new infrared observations pierce through this transformation, capturing light from galaxies at virtually any distance in the observable sphere. What appeared empty in visible wavelengths blazes with structure in infrared. Dusty regions where stars form, previously opaque to optical observation, become transparent. Galaxies hidden behind cosmic dust clouds reveal themselves. The darkness between bright sources fills with fainter objects, countless systems too distant or too obscured for earlier instruments to detect. The night sky, already crowded with galaxies in long-exposure visible light photographs, becomes almost incomprehensibly dense when observed at longer wavelengths. Nearly everywhere astronomers point their infrared detectors, they find galaxies stacked behind galaxies, layer upon layer receding toward the cosmic horizon. But distance creates distortions that go beyond simple wavelength shifts. The expansion of space affects how we perceive time in distant regions. According to relativity, objects moving at high velocities relative to an observer experience time at different rates. Galaxies at the edge of the observable universe recede at speeds approaching the velocity of light due to cosmic expansion. From our reference frame, time in those distant systems appears to slow. We see them frozen at particular moments in their evolution, watching light that depicts events occurring billions of years ago, while those galaxies have continued evolving in ways we cannot yet observe. The most distant objects appear suspended at the moment they crossed our cosmic horizon, their subsequent history still traveling toward us through expanding space, stretched and dimmed by the journey. This creates a peculiar situation where observation and reality diverge. We witness the universe's past wherever we look. Nearby galaxies appear as they were millions of years ago. Distant galaxies appear as they were billions of years ago. The most remote structures visible show us the cosmos in its infancy, barely recognizable compared to its current state. Yet all of these objects exist now in forms we cannot yet see, evolved beyond what their ancient light reveals. We inhabit a universe filled with fossils, frozen images of systems that have long since transformed or disappeared. The present moment of the cosmos remains partially hidden, obscured behind the finite speed of light and the vast distances that separate one region from another. And still, even with this understanding, even with the most sophisticated instruments positioned beyond Earth's atmosphere to eliminate distortion and interference, we see only a fraction of what exists. The observable universe represents merely the portion of space where light has had time to reach us since the beginning. Beyond 46 billion light-years in every direction lie regions that remain forever invisible, not because they lack galaxies or structure, but because cosmic expansion prevents their light from ever completing the journey. Space expands faster than light can cross it at those distances. Photons travel toward us, but the gulf between us widens faster than they can traverse it. Those regions exist in complete causal disconnection from our own, unable to send signals or information across the accelerating expansion that separates us. The universe does not end at our horizon. Space continues indefinitely, potentially stretching infinitely in all directions. Every observable sphere surrounding every possible vantage point reveals different galaxies, different structures, different subsets of the total cosmic population. An observer 50 billion light-years away would see galaxies invisible to us. They would catalog a cosmos as rich and complex as the one we observe, yet their census would overlap with ours hardly at all. We inhabit one bubble of observability in an expanse that contains countless such bubbles, each centered on different locations, each revealing truths that others cannot access. What lies beyond our horizon? More of what we see here. Presumably, the laws of physics appear universal within our observable region. No evidence suggests they change with distance or direction. The cosmological principle asserts that the universe looks roughly the same everywhere when averaged over sufficiently large volumes. Our location seems typical, not special. If this holds true, then regions beyond our horizon host similar densities of galaxies, similar structures, similar processes unfolding across billions of light-years. But we cannot prove this. It remains an assumption based on symmetry and simplicity rather than direct measurement. Perhaps distant regions differ dramatically. Perhaps different physical constants apply there. Perhaps entirely different forms of matter and energy dominate beyond the edge of what we can observe. These questions border on philosophy rather than science, addressing aspects of reality that might be fundamentally inaccessible to empirical investigation. Yet they emerge naturally from what we can measure and confirm. The observable universe, vast almost beyond comprehension, represents only what light has had time to reveal. The total universe, the complete structure of existence, extends farther by amounts we cannot currently determine. It might be 10 times larger. It might be 1,000,000 times larger. It might be infinite, containing endless repetitions of structures and patterns in all possible configurations. Every new observation refines our understanding, but also deepens the mystery. We thought we were approaching a complete picture of the cosmos, a final accounting of how much exists and where it formed and when it began shining. Instead, each advance in observational capability reveals more than we anticipated. Structures appearing earlier than predicted, populations denser than expected, scales larger than theory suggested. The universe resists easy categorization. It exceeds our models at every turn. What we thought was comprehensive turns out to be preliminary. What we believed was nearly complete proves to be barely started. The journey into the universe's true scale does not end with distance and number. It reaches into something more unsettling. The sense that reality itself might not be what it seems, and that everything we experience is filtered through a system that was never designed to show us the truth. Every day, without effort, the world appears stable and solid. The floor feels firm under your feet. The coffee mug sits reliably on the table. The sky arches overhead as a blue dome, the sun tracing a predictable path from horizon to horizon. The mind takes this consistency as evidence that what is seen is what is there. Reality feels like an external stage populated by objects that exist independently of you, waiting to be discovered by anyone who looks. Your eyes, ears, and brain feel like windows opening directly onto that world. Yet this sense of direct access is an illusion, one built carefully and efficiently by a biological system whose only goal is survival. Light from distant objects enters your eyes as streams of photons that have no intrinsic color. Sound waves reach your ears as variations in air pressure without inherent pitch or tone. Molecules strike receptors in your nose and mouth without any built-in smell or taste. Your brain takes these raw physical signals and transforms them into a movie of experience. Colors, sounds, shapes, textures, emotions. It does not show you electromagnetic frequencies, pressure gradients, or molecular structures. It shows you a simplified interface, a user-friendly layer of icons that hide the underlying complexity of the world. A ripe fruit appears red and inviting, not because redness exists in the fruit, but because your nervous system assigns that experience to a particular pattern of reflected wavelengths that historically signaled nutrition and energy. This idea that perception functions like a user interface rather than a window has profound consequences. When you use a smartphone, you do not see the electrons flowing through circuits or the machine code executing in the processor. You see icons, buttons, and images that stand in for something far more complex and inaccessible. The interface is useful precisely because it hides what is really happening. If you had to think in terms of voltages and memory addresses to send a message or open a photo, the device would be nearly impossible to operate. Instead, you tap simple symbols that compress complex processes into manageable actions. Perception might be doing something similar. The brain shows you colors, objects, and spatial layouts because those are efficient representations for guiding behavior, not because they reveal the true structure of reality. This perspective reframes what seeing the universe means. When telescopes capture light from distant galaxies, that light still must be interpreted by human observers. Detectors convert photons into electrical signals. Computers process those signals into images. Scientists then translate those images into colors humans can perceive. Infrared light, radio waves, and X-rays are mapped into visible hues so the mind can make sense of them. What ends up on the screen is not a literal picture of the universe as it exists in itself, but a representation crafted to fit a creature with very particular sensory limitations. The cosmos we marvel at in deep-field images is already filtered through multiple layers of translation and interpretation before it ever reaches human awareness. If perception is an interface, the most important question shifts from, "Is what I see real?" to, "What is this representation for?" Biological systems do not evolve to perceive the truth, they evolve to perceive what helps them survive and reproduce. Seeing water as transparent and fluid is useful. Seeing its quantum wave functions or molecular orbital structures is not. The organisms that thrived were those that reacted quickly and appropriately to simplified cues, not those that paused to contemplate deeper physical realities. Over millions of years, this pressure sculpted brains that trade accuracy for efficiency. The result is a species that experiences a coherent, meaningful world without any direct insight into the substrate that generates it. This is why it feels natural to imagine space as a giant three-dimensional container sprinkled with objects, planets, stars, galaxies. That picture works for navigation and everyday intuition, but modern physics suggests that space and time themselves might be emergent constructs, high-level descriptions arising from something more fundamental that does not resemble our familiar notions of distance and duration. In the same way that temperature emerges from the motion of countless particles and does not exist at the level of single atoms, space-time may emerge from deeper, invisible relationships that our senses and intuitions are not built to perceive directly. The evidence for this comes from multiple directions. Quantum mechanics describes particles not as tiny billiard balls moving through space, but as excitations of underlying fields, probability amplitudes spread out across regions of space-time. In these theories, what we call a particle is essentially a ripple in an invisible ocean. The classical picture of objects with definite positions and trajectories breaks down at fundamental scales. Different experiments yield results that defy everyday categories, forcing physicists to describe nature using mathematical structures that have no direct sensory analogy. Reality at its smallest scales refuses to behave like the solid, continuous world our perceptions depict. Even the concept of a field is itself an abstraction, a mathematical object that helps predict outcomes. The deeper questions remain unresolved. Is the universe ultimately made of quantum fields, or are fields another layer of description sitting atop a more fundamental level based on information, relationships, or something even more abstract? Some researchers propose that space-time emerges from patterns of entanglement, the strange connections that allow separated quantum systems to behave as a unified whole. In these models, geometry, the shape and curvature of space is not fundamental, but arises from how information is organized and shared at the tiniest scales. This idea that information might be more basic than matter or space appears in multiple corners of modern physics. Black hole thermodynamics, for example, connects the surface area of a black hole's event horizon to the amount of information it can encode. Quantum theory links probabilities and measurement outcomes to information about systems rather than to objects with pre-existing properties. The famous paradoxes surrounding black holes in quantum mechanics often reduce to questions about whether information can be destroyed, how it moves, and what it means for information to be preserved or scrambled in extreme environments. If information really does sit at the foundation of physical reality, then perception, our interface with the world, is a system for extracting, compressing, and using information in a way that maximizes survival, not a transparent window showing us the information's true form. Once this is recognized, even basic questions become strange. When you look at a distant galaxy, what exactly are you seeing? You are not interacting with the galaxy as it currently exists, billions of light years away. You are interacting with photons that left that galaxy billions of years ago. Photons that have been stretched, redshifted, and diluted by the expansion of space. The signal you receive is a faint whisper from a long-gone moment, processed by detectors and transformed through algorithms into an image on a screen, which is then interpreted by your brain according to rules it never chose and does not consciously control. At every stage, something is being translated, simplified, or discarded. The same logic applies to your own body. The sense of having a stable, unified self occupying a physical form is itself a construction. Your brain continuously integrates signals from internal organs, muscles, joints, and skin, creating a model of me that feels seamless and persistent. In reality, the body is a roiling system of atoms exchanging with the environment, molecules entering and leaving, cells dividing and dying. The atoms that make up your body today were part of stars, planets, gas clouds, and other organisms in the past. They will drift elsewhere in the future. The boundary between you and the universe is a convenient fiction, drawn by perception to separate what is under partial control from what is not. Modern cosmology amplifies this insight by showing that the material that forms your body was forged in stars that lived and died billions of years ago. The carbon in your cells, the oxygen in your blood, the calcium in your bones all were assembled in thermonuclear reactions inside stars, then scattered into space by explosive deaths. These atoms drifted through the galaxy, became part of gas clouds, then planets, then oceans, then living cells. The universe did not create you as something separate from itself. It reorganized old material into a pattern that can observe and reflect. The sense that you are an observer standing apart from the cosmos is another artifact of the interface, another illusion generated for functional reasons. This raises an unsettling possibility. If perception is an interface tuned for survival, and physics suggests that the deepest layers of reality are nothing like the world we experience, then nearly everything that feels obvious about existence might be a carefully constructed story. The solidity of matter, the flow of time, the division between self and world, even the notion of an objective, observer-independent universe out there may all be approximations useful, powerful, but incomplete. They work extraordinarily well for navigating daily life and building technology. Yet they may conceal more than they reveal. Complicating this further are the competing interpretations of quantum mechanics, each offering a different picture of what is ultimately real. In some views, the wave function, a mathematical object encoding probabilities, represents a physical entity that collapses upon measurement, implying that observation plays a special role in determining outcomes. In others, the wave function never collapses, and every possible outcome actually occurs in branching versions of reality. Still, other approaches argue that the wave function is merely a tool for predicting measurement results, not a real thing, and that underlying variables determine outcomes in ways we have not yet uncovered. Each interpretation preserves the same experimental predictions, yet paints a radically different picture of what the universe is. This divergence underlines a sobering fact. Mathematics can describe regularities in observations without telling us what those regularities are made of. Equations can predict how particles will behave without revealing what a particle really is. Models can forecast how galaxies cluster without answering what space fundamentally consists of. The map can be incredibly accurate while remaining silent about the exact nature of the territory. For a species that experiences reality through a heavily filtered interface, this may be the best that can be achieved. Increasingly precise maps, increasingly subtle models, all pointing toward a landscape that cannot be perceived directly. And yet, there is something extraordinary in this limitation. The same interface that hides the world's deepest layers also allows you to ask questions about them. A brain built from stardust, running on electrochemical signals, surrounded by a universe it cannot fully see, has found ways to infer patterns and structures that exist far beyond its native sensory range. Instruments extend perception into wavelengths no creature evolved to detect. Mathematics extends intuition into domains no sense organ can access. Philosophy interrogates the assumptions built into every experience, asking what it means for anything to exist at all. In this light, the discoveries of the modern cosmos, galaxies that formed too early, black holes that grew too fast, a universe that is larger, older, and more intricate than expected are not just scientific puzzles. They are mirrors held up to the mind, revealing the limits of the stories perception tells about reality. Each surprising observation is a reminder that the interface is not the territory, that what feels solid and obvious may be provisional and fragile. The universe is stranger than the icons our senses show us. The true scale of what exists, and of what might exist beyond our horizon, forces a reconsideration not only of the cosmos, but of what it means to see, to know, and to be. The question becomes unavoidable. If perception is an interface, what lies beneath it? What is the universe actually made of when you strip away the colors, shapes, and objects that consciousness projects onto raw physical processes? Physics offers an answer, but it is not the one intuition expects. At the most fundamental level accessible to current science, reality does not consist of tiny solid objects arranged in space. It consists of fields and visible substrates filling every point of the universe, vibrating and interacting according to mathematical laws. These fields are not made of anything more basic. They simply are. An electron is not a miniature sphere orbiting an atomic nucleus like a planet around a star. It is an excitation in the electron field, a localized pattern of energy that behaves in some contexts like a particle and in others like a wave. The same applies to every other fundamental entity: quarks, photons, neutrinos, even the recently confirmed Higgs boson. All are ripples in their respective fields. This picture emerged gradually over the 20th century as physicists probed matter at smaller and smaller scales. Early experiments suggested that atoms were the smallest units of matter, indivisible building blocks from which everything else was constructed. Then scientists discovered that atoms themselves had internal structure, a nucleus surrounded by electrons. The nucleus turned out to be made of protons and neutrons. Protons and neutrons, in turn, are composed of quarks bound together by particles called gluons. At each level, what seemed elementary revealed deeper complexity. Yet this descent did not continue indefinitely. Eventually, researchers reached a layer where the components no longer appear to have internal parts. Quarks, electrons, and photons show no evidence of being made from smaller constituents. They behave as point-like entities, at least within the resolution of current experiments. But calling them particles is misleading. Quantum field theory, the mathematical framework describing these entities, treats them as disturbances in underlying fields. The electron field permeates all of space. When energy concentrates in a particular region of this field, we observe what we call an electron. The photon field underlies light and all electromagnetic radiation. Ripples in this field carry energy from one place to another, and we perceive those ripples as particles of light. The universe, from this perspective, resembles an ocean. Individual waves and ripples come and go, but the ocean itself remains, a continuous medium from which all observable phenomena arise. What makes this especially strange is that fields do not exist in space the way objects sit on a table. Space itself might be a property of the fields or an emergent description arising from how fields interact. Some versions of quantum gravity suggest that space-time is not a fundamental stage on which physics unfolds, but rather a derived concept that appears only when you average over countless quantum interactions. At the deepest level, there may be no distance, no duration, no separation between events, only a web of relationships encoded in abstract mathematical structures. Space-time, the arena that seems so basic and undeniable, could be an approximation that holds at human scales, but dissolves when examined with sufficient precision. This idea finds support in studies of black holes and cosmology. Black holes warp space-time so severely that familiar notions of distance and time break down near their event horizons. At the singularity, where matter collapses to infinite density according to classical general relativity, the equations produce nonsensical predictions. Most physicists interpret this as a sign that general relativity is incomplete, that a more fundamental theory, quantum gravity, will resolve the singularity by revealing new structure at scales smaller than anything currently observable. That new structure might not involve space and time as we understand them. It might involve networks of quantum entanglement, loops of geometry, or strings vibrating in higher dimensional spaces. Each of these approaches dispenses with the intuitive picture of reality and replaces it with something deeply abstract. Quantum mechanics itself resists intuitive interpretation. Consider the famous double-slit experiment. Fire particles one at a time toward a barrier with two narrow openings. On a screen behind the barrier, the particles accumulate in a pattern of alternating bright and dark bands, as if each particle interfered with itself by passing through both slits simultaneously. Close one slit, and the interference pattern disappears. The particle behaves differently depending on whether it could have taken two paths, even when only one particle is present at a time. Measure which slit the particle passes through, and the interference vanishes again. The act of measurement changes the outcome. Reality seems to respond to what is observed, refusing to commit to a definite state until something forces it to choose. Physicists have developed multiple ways of interpreting this behavior. The Copenhagen interpretation treats the wave function, the mathematical object describing probabilities, as a complete description of reality before measurement, then says the wave function collapses when observed, selecting one outcome from many possibilities. This interpretation leaves unanswered what counts as a measurement and what causes collapse. The many-worlds interpretation avoids collapse by proposing that every possible outcome actually occurs, but in separate branches of reality that cannot communicate with each other. From this view, the universe constantly splits into countless parallel versions, each realizing a different possibility. A third approach, pilot wave theory, restores determinism by proposing that particles have definite positions guided by a hidden wave, though this requires accepting faster than light influences that do not transmit information. Each interpretation preserves the same experimental predictions, but implies a radically different ontology. In one, measurement is a mysterious process that fundamentally alters reality. In another, the universe branches endlessly, and observation merely reveals which branch you inhabit. In a third, hidden variables determine everything, and probability reflects ignorance rather than fundamental randomness. No experiment has yet distinguished between these views. They remain competing narratives, different stories about what the mathematics represents. The equations work, the meaning remains contested. This ambiguity extends to the nature of particles themselves. In quantum field theory, what we call a particle depends on how we choose to measure the field. Different observers in different states of motion can disagree about how many particles are present in a given region. One observer might detect a vacuum, no particles at all, while another detects particles being created and annihilated. The notion of a particle becomes observer-dependent, a feature of how certain measurements carve up the field rather than an objective property the field possesses independently. This hints that particles, like colors and sounds, might be elements of the interface rather than features of the underlying reality. Some physicists go further and suggest that information, not matter or energy, is the most fundamental substrate. This idea appears in multiple guises. John Wheeler, one of the pioneers of quantum gravity, proposed it from bit, the notion that every physical quantity derives ultimately from yes or no questions, from binary distinctions encoded in the structure of reality. In this view, the universe is not a collection of things described by information. It is information, and things are patterns in that information. Evidence for this perspective comes from black hole thermodynamics. When matter falls into a black hole, it seems to disappear from the universe, taking its information with it. But the laws of quantum mechanics suggest that information cannot be destroyed, only transformed or redistributed. This creates a paradox. If black holes destroy information, quantum mechanics is violated. If they preserve it, where does the information go? Stephen Hawking initially argued that information was lost, but later research suggested it might be encoded on the black hole's event horizon, the boundary beyond which nothing can escape. The amount of information a black hole can store turns out to be proportional to the surface area of its event horizon, not its volume. This strange result implies that three-dimensional space might be a hologram, a projection of information stored on a two-dimensional surface. The holographic principle, as it is called, has been developed into a precise mathematical framework in certain models of quantum gravity. In these models, everything happening inside a volume of space can be fully described by data encoded on the boundary of that volume. The interior is redundant, a derived description that adds no new information. This suggests that the three-dimensionality of space is not fundamental but emergent, arising from relationships and correlations in a lower dimensional structure. Space, from this perspective, is an illusion, a useful way of organizing information, but not a primary feature of reality. Entanglement, the phenomenon where two quantum systems remain correlated even when separated by vast distances, also hints at information as fundamental. When particles become entangled, measuring one instantly affects the outcome of measuring the other, regardless of how far apart they are. This does not allow faster than light communication, but it does mean that the particles share information in a way that defies classical explanation. Some researchers propose that space-time itself is woven from entanglement, that the geometry of space emerges from patterns of quantum correlations. In this picture, distance is a measure of how entangled two regions are. Strongly entangled regions appear close. Weakly entangled regions appear distant. Space is not a container. It is a map of information relationships. If this is correct, then asking what reality is made of might be the wrong question. Reality might not be made of anything in the usual sense. It might be structured information, patterns of correlation and causation obeying mathematical rules. What we perceive as matter, energy, space, and time could all be high-level descriptions of how information organizes and flows. The universe, at its core, might resemble a computation more than a machine, processing inputs according to fixed algorithms and generating outputs that we interpret as physical events. This computational view finds resonance in certain interpretations of quantum mechanics and in the structure of physical laws themselves. The equations governing quantum fields, general relativity, and thermodynamics all describe how information propagates and transforms. Conservation laws ensure that certain quantities remain constant, which is equivalent to saying that certain types of information cannot be created or destroyed. Symmetries in the laws invariance under rotations, translations, and time shifts reflect deep constraints on how information can be encoded and manipulated. The entire edifice of physics can be recast as a theory about what kinds of information processing are allowed and what kinds are forbidden. Yet even this perspective remains a description, another layer of abstraction built atop something we cannot access directly. Information requires a medium, a substrate in which it is encoded. Bits of data do not float freely in a void. They exist as configurations of physical systems. If information is fundamental, what is it information about? And what processes the information, determining how it evolves from one moment to the next? These questions push against the limits of scientific inquiry, entering territory where physics blurs into metaphysics, and the tools of measurement reach the edge of their applicability. This brings the discussion back to perception and consciousness. If the universe is structured information, then observation, the act of extracting information from a system, takes on special significance. In quantum mechanics, measurement is not a passive recording. It is an interaction that affects both the measured system and the observer. The observer does not stand outside reality looking in. The observer is part of the system, entangled with what is being measured. This erases the clean division between subject and object, between the one who knows and the thing that is known. Consciousness itself remains one of the deepest mysteries. Neuroscience can map brain activity, identify which regions activate during different tasks, and describe how neurons communicate through electrical and chemical signals. But it cannot explain why those processes give rise to subjective experience, to the sensation of being someone who perceives and feels. The so-called hard problem of consciousness asks why there is something it is like to be you, why the physical interactions in your brain are accompanied by an inner life. No current theory provides a satisfying answer. The activity of neurons seems entirely describable in terms of chemistry and electricity, yet somehow that activity produces the vivid, immediate sense of seeing red, hearing music, or feeling pain. Some philosophers argue that consciousness cannot be reduced to physical processes, that subjective experience is a fundamental feature of reality not captured by physics. Others propose that consciousness is an illusion, a story the brain tells itself, with no independent existence beyond the patterns of neural firing that generate it. Still, others suggest that consciousness might be widespread, a property of all information processing systems to varying degrees, rather than something unique to biological brains. Each position has defenders and critics, and no consensus has emerged. What seems clear is that perception and reality do not map onto each other transparently. The brain constructs experience from incomplete data, filling in gaps, smoothing over inconsistencies, and presenting a coherent narrative even when the underlying information is fragmentary. You experience a seamless visual field, but your eyes constantly move, fixating on small regions while peripheral vision remains blurry. Your brain stitches together these snapshots into a stable image, hiding the motion and the blind spots. You experience time as flowing smoothly, but neural processing takes time, and different senses have different delays. Your brain synchronizes these signals, creating the impression of simultaneous events even when they occur at slightly different moments. All of this suggests that the world of conscious experience is a model, a simulation running in the brain, optimized for action rather than accuracy. The universe you experience is not the universe that exists independently of observers. It is a species-specific, individual-specific rendering shaped by evolutionary history and neural architecture. Other organisms experience different renderings. A bat perceives the world through echolocation. A bee sees ultraviolet patterns invisible to humans. A dog smells chemical gradients that human noses cannot detect. Each species inhabits its own perceptual reality, its own interface with the underlying physics. There is no neutral view from nowhere, no perspective that captures reality as it truly is. This realization does not undermine science. It clarifies what science accomplishes. Science builds models that predict observations, that relate measurements to one another through mathematical structures. It does not claim to reveal the universe as it exists apart from all measurement and observation, because such a revelation may be impossible. Instead, it maps the regularities within experience, finding patterns that hold across observers and contexts. Those patterns point towards something beyond experience, something that constrains and shapes what can be observed, but the thing in itself remains inaccessible, knowable only through its effects on the interface. Imagine looking up at the night sky and realizing that every star, every galaxy, every shining cluster is not just far away in space, but far away in time, and that your own mind is quietly inventing a world on top of that ancient light. The universe is not only bigger and stranger than it appears, the very act of appearing may be one of its most mysterious tricks. There is a tension at the heart of modern thought. On one side, a physical cosmos described by mathematics, fields, information, and quantum rules. On the other, a lived world of colors, sounds, meanings, and memories. The two seem intimately linked yet fundamentally different. Equations describe energy levels and wave functions. Consciousness knows the taste of coffee and the ache of loss. Physics explains how galaxies form and stars explode. The mind experiences awe beneath a dark sky. Any attempt to grasp reality now has to navigate between these two domains, the impersonal patterns of nature and the first-person perspective that witnesses them. From one angle, the human mind looks like a small, temporary fluctuation in a vast sea of matter and energy. The atoms in your brain obey the same laws as the atoms in a distant nebula. They were forged in ancient stars, scattered across space, gathered into clouds, and eventually assembled into a nervous system capable of wondering where it came from. From another angle, the mind is the only place anything like meaning exists. Without conscious observers, there would still be stars and galaxies, but there would be no questions, no curiosity, no sense of mystery. The universe would be, but it would not be known. This leads to a deep philosophical puzzle. Is the universe fundamentally a mindless structure that incidentally gives rise to consciousness? Or is consciousness somehow woven into its basic fabric? Most scientists lean toward the first view, a physical cosmos that, under the right conditions, produces biological organisms with complex brains. And those brains generate subjective experience as an emergent property. In this picture, mind is a latecomer, a delicate flame lit in the last fractions of cosmic history. The physical world is primary, awareness appears as a side effect. Yet, the more closely experience is examined, the more it refuses to be treated as a mere byproduct. Every fact about the universe, every measurement, every observation is ultimately registered in some conscious system. Even when instruments collect data automatically, the result becomes meaningful only when a mind interprets it. The entire edifice of science rests on patterns in conscious experience. Instrument readings, visual images, statistical plots, shared descriptions. The physical universe might exist independently of observation, but everything known about it lives inside experience. That dependence makes some philosophers question whether mind can be dismissed as secondary. Several broad positions have emerged in response to this tension. One is physicalism, the idea that everything, including consciousness, is ultimately physical. On this view, once the brain is understood completely, subjective experience will be explained in terms of neural activity, much as temperature is explained in terms of molecular motion. Another position is dualism, which holds that mind and matter are fundamentally different kinds of things, interacting but irreducible to one another. A third family of views, sometimes called panpsychism or neutral monism, suggests that the basic ingredients of reality are neither purely mental nor purely physical, but something deeper from which both emerge. None of these approaches has achieved decisive victory. Physicalism struggles to explain why neural processes should produce inner experience at all, rather than functioning as complex but unconscious computations. Dualism struggles to explain how two utterly different substances could interact without violating conservation laws. Panpsychist-style views struggle to explain how countless tiny proto-experiences could combine into the unified consciousness you inhabit. Every position offers insight and generates new questions, and each aligns differently with the picture of a universe built from fields and information. Meanwhile, physics marches forward, largely indifferent to these debates, refining models that predict observations with astonishing precision. Cosmology traces how tiny quantum fluctuations in the early universe seeded the formation of galaxies. Simulations show how dark matter filaments grow, how gas cools and collapses, how stars ignite, live, and die. Measurements of the cosmic microwave background, the afterglow of the Big Bang, reveal a universe that is mostly dark energy and dark matter, with ordinary matter making up only a small fraction of the total. None of these calculations mentions consciousness. They do not need to in order to work. Yet there is a subtle connection. The laws of physics do not refer to observers, but quantum mechanics does refer to measurements, and measurement always involves some kind of interface. It may be a human eye, a CCD sensor in a telescope, or a complex array of detectors in a laboratory. In each case, a physical system interacts with another system, and the interaction produces a definite outcome recorded as information. What looks, at the human scale, like seeing a galaxy is, at the microscopic scale, a cascade of quantum events that end in a particular pattern of neural activity. The interface theory of perception suggests that what consciousness receives at the end of this chain is not the world as it is, but a species-specific rendering optimized for survival. This rendering has remarkable properties. It hides almost all of the underlying physics, compresses vast amounts of information into manageable forms, and emphasizes only what matters for action. A distant galaxy becomes a faint smudge or a bright point of light, not a full representation of its trillions of stars, its black holes, its chemical composition, or its internal dynamics. Even the Earth beneath your feet is presented as a solid, continuous surface, despite being mostly empty space between atomic nuclei and electron clouds. The interface gives you what you need to walk, grasp, speak, and cooperate, not what you would need to see quantum fields or the curvature of space-time. One way to think about this is to imagine two overlapping realities. The first is the physics reality: quantum fields, entanglement, dark matter, dark energy, space-time geometry, thermodynamic flows. The second is the phenomenal reality: colors, sounds, objects, people, emotions, stories. The first is described by equations and tested by experiment. The second is lived directly, without calculation. The two are linked by the body and brain, which translate one into the other. When light from a distant galaxy hits your eye, physics describes the path of photons through expanding space. Phenomenal reality presents a tiny luminous speck against a dark backdrop. Both descriptions refer to the same event, but at different levels. The universe revealed by telescopes pushes against the limits of both realities. In the physical description, there are galaxies that should not exist yet, black holes that should not be so massive so early, structures that should not have grown so quickly in the available time. The equations fit most observations, but these anomalies hint that something is missing, some ingredient not yet accounted for. In the phenomenal description, there is the sensation of awe, the sense of standing on a small world orbiting an ordinary star, confronted with vastness and mystery. That feeling does not appear in any equation, but it is as real to you as any measurement. These two perspectives converge most sharply when the implications of cosmology are applied to the self. The atoms in your body are ancient, forged in generations of stars. The time it took for those stars to form, live, and die is written into their composition. The iron in your blood testifies to supernovae that exploded billions of years ago. The calcium in your bones carries the history of stellar cores that quietly fused lighter elements into heavier ones. When you look at a deep field image containing hundreds of thousands of galaxies, you are seeing the environments that made your existence possible. Some of those galaxies are ancestors in a chemical sense, factories that produce the elements that would eventually assemble into you. At the same time, the brain that perceives this is transient. Neural circuits that took millions of years to evolve can be disrupted in seconds by injury, chemicals, or disease. Memories fade. Attention wanders. The sense of self, which feels so continuous and solid, is in fact a process renewed moment by moment. In a few decades, every neuron now active will be gone, replaced, or disintegrated, and the pattern that supports your experience will have vanished. The matter will remain in some other form, following the same physical laws, but the particular arrangement that called itself you will dissolve. Seen through the lens of physics, this is unsurprising. Structures form, persist for a while, and decay. Stars do it, galaxies do it, clusters do it. Conscious beings are no exception. Seen through the lens of experience, it is deeply personal. Questions arise. If everything that makes up me is temporary and made from repurposed star stuff, what exactly am I? A pattern? A process? A story the brain tells itself? And if so, what does it mean that this pattern is capable of contemplating the entire observable universe? Some philosophical views lean into this pattern-based identity. They suggest that what matters is not the specific atoms or even the specific neurons, but the organization, the flow of information, the relationships between states. In this view, you are a structured process running on the substrate of the brain, in the same way that software is a structured process running on a computer. Change the hardware, keep the organization, and in principle, the process could continue. This raises speculative possibilities about mind uploading or artificial consciousness, but it also raises a subtler point. The boundary between self and world is not as sharp as the interface suggests. The brain's patterns are continuously shaped by the environment. Every experience modifies synaptic connections, strengthens some pathways, weakens others. Culture, language, relationships, and knowledge all leave traces in neural structure. The universe is not just outside you, it is also inside you, encoded in the pathways that formed in response to sensory input over a lifetime. The night sky you see is not just a physical arrangement of distant suns. It is a mental construction shaped by stories heard as a child, images seen in textbooks, explanations offered by teachers and documentaries. Your sense of the universe is as much a cultural artifact as it is a physical perception. This intertwining of inner and outer suggests a different way of thinking about the universe's true scale. It is not only a matter of light years and galaxy counts, of metrics and curvature. It is also a matter of conceptual reach, how far the mind can stretch to imagine, model, and find meaning in what is observed. A prehistoric human saw the night sky as a dome studded with lights. A modern observer sees it as a cross-section of space-time, a view into the distant past filled with billions of galaxies. The physical sky has not changed in any fundamental way. The conceptual sky has expanded enormously, and that expansion is ongoing. The discovery that the observable universe is 93 billion light-years across reshapes intuition. The realization that space itself is stretching, that galaxies beyond a certain distance are receding faster than light due to expansion, challenges naive ideas of motion and distance. The recognition that most of the universe is made of dark energy and dark matter entities that cannot be seen directly forces a rethinking of what it means to exist. Each of these insights pushes perception's interface further from its evolutionary roots, extending it with tools, theories, and metaphors. In this sense, the human project of understanding the cosmos is an attempt to rewrite the interface from the inside. Telescopes, detectors, particle accelerators, and equations are all ways of hacking perception, of training the brain to see beyond its default settings. When you look at an image of a deep field, you are not just seeing a picture, you are seeing a translation. Invisible infrared light has been mapped into visible colors. Enormous differences in distance and brightness have been compressed into a manageable form. Annotations and scales add layers of meaning. Your mind, primed by explanation, learns to interpret the smudges and points as entire galaxies, each with its own history and internal complexity. The result is a kind of double vision. On one level, you see colored dots and shapes on a screen. On another, you see the unimaginable distances, the ancient light, the chemical enrichment, the star formation, the black holes, the mergers, and the voids. Part of you still lives in the ancestral interface, where the sky is just what it looks like. Another part has been educated into a cosmic perspective, where what you are really looking at is a fossil record of a universe evolving over billions of years. The same photons produce both experiences. The difference lies in how the brain interprets them. This double vision can change how life on Earth is experienced. Daily concerns, deadlines, arguments, minor successes, and failures do not disappear, but they become framed against a backdrop measured in billions of light years and billions of years. The scale of the universe does not make human life meaningless. It reveals that meaning is something created locally, within tiny pockets of order that briefly arise in a largely indifferent cosmos. The fact that conscious beings exist at all, on one small planet, around one ordinary star and one galaxy among trillions, is itself astonishing. The universe spends most of its time and space in silence. For a brief period, in a few scattered locations, it wakes up. To recognize this is not to diminish the self, but to place it. You are not separate from the universe, looking out at it from the outside. You are a particular arrangement of the universe looking at itself. The atoms that form your eyes were once in stars. The photons entering those eyes began their journeys millions or billions of years ago. The brain interpreting those photons uses patterns shaped by evolution, culture, and personal history. The awe you feel is the universe's reaction to its own depth. In the end, the true scale of the universe is not just a number or a distance. It is a relationship between the immensity of what exists and the narrow channel through which it is perceived. That channel can be widened, but never infinitely. There will always be horizons, things too distant to see, times too long to imagine, structures too complex to fully grasp, aspects of reality too fundamental to be rendered within the human interface. Yet within those limits, there is room for wonder. The cosmos may be more than perception can ever capture, but the part that does appear is enough to transform how existence is understood and how fleeting, fragile, and precious a single conscious life can be. There is another layer to this story, one that moves from the vastness of galaxies and the strangeness of quantum fields to the questions that sit quietly behind everyday life. What is real? What is you? And how should a tiny conscious being live inside a universe that seems both indifferent and astonishing? For most people, reality feels simple, even if the details are unknown. There is a physical world out there, composed of objects that exist whether or not anyone observes them. There are other people, each with their own minds. There is a body that you inhabit, a stream of thoughts and feelings that you call me, and a timeline stretching from birth to death. Within that picture, science is usually imagined as a kind of polishing process, gradually removing errors and illusions until what remains is a more accurate version of the same basic world. The universe gets bigger, older, and more detailed, but the core idea stays the same. A mind-independent reality being gradually uncovered. Yet many of the most provocative ideas in modern physics and philosophy suggest that this common-sense picture is at best incomplete, and at worst deeply misleading. On one side are forms of realism that insist the universe has a definite structure independent of observers, and that our theories approximate that structure more and more closely. On the other side are views that question whether our concepts of objects, space, and even existence make sense outside of our perceptual and conceptual framework. Between them run multiple variations. Some see reality as fundamentally physical, some as fundamentally mental or informational, and some as a hybrid. One strong version of realism holds that the universe consists of fundamental entities, fields, particles, space-time, or perhaps something even more basic, organized by mathematical laws. Our sensory experiences are then byproducts of particular physical arrangements. The job of science is to discover those laws and entities, while philosophy clarifies what they imply. According to this view, galaxies, black holes, dark matter, and quantum fields are all parts of an objective structure that would be there even if no conscious beings existed. What perception shows is a filtered, approximate version of this structure, but the structure itself is mind-independent. Against this, anti-realist perspectives argue that much of what is taken as real is actually a feature of models and descriptions rather than of the world itself. Quantum mechanics, for example, gives rules for predicting measurement outcomes, but it does not specify what the world is doing between measurements. Some philosophers and physicists, therefore, treat the wave function not as a physical object, but as a tool encoding probabilities. The reality, on this view, might be nothing more than the network of observed regularities, plus the mathematical formalism used to track them. Talk of fields or particles becomes a convenient way of speaking about patterns in observation, not about hidden entities existing behind them. Then there are simulation-like ideas, which suggest that what is experienced as physical reality could be the product of some deeper informational or computational process. In these views, the equations of physics describe rules of an underlying program. Space might be a grid of information points. Time might be a sequence of updates. What appears continuous and analog could be discretized at a deeper level. This does not necessarily mean that the universe is literally running on a computer built by some advanced civilization, but it does suggest that computation and information processing might be more fundamental than matter in motion. Another family of theories treats space-time itself as emergent. In some models, space arises from patterns of entanglement in an underlying quantum system. The connectivity of that system, how strongly different parts are correlated, determines the geometry we experience as distance and curvature. Under this view, the great cosmic structures revealed by telescopes are high-level manifestations of deeper, hidden relationships. The cosmic web, with its filaments and voids, might be the large-scale expression of entanglement patterns writ across unimaginable numbers of degrees of freedom. Space is no longer a passive stage. It is an emergent consequence of how information is organized. These interpretations and frameworks sometimes collide, sometimes overlap. Realists argue that something must exist in its own right to explain the stability and regularity of observations. Anti-realists counter that positing an unseen world beyond all possible observation may be metaphysical excess. Simulation or information-based views propose that what is real is not matter or mind alone, but the structure of relations and transformations that can be captured in precise rules. Emergent space-time theories insist that our intuitions about distance, location, and even causality may be artifacts of a particular level of description. Into this already complex landscape step questions about the self. Neuroscience treats you as a process running in the brain, a dynamic pattern arising from neural interactions. Philosophical traditions, both ancient and modern, have suggested similar things in different language. The self as a story, a bundle, a temporary pattern of thoughts and sensations. If this is right, then the solid sense of being a single, enduring subject is itself one of the interface's most powerful illusions. Your name, memories, personality traits, and preferences all feel like parts of a stable entity, but beneath them lies constant change, new neural connections forming, old ones weakening, thoughts arising and fading moment by moment. From a cosmic perspective, this pattern-based self is exceedingly fragile. It depends on a narrow range of physical conditions: stable temperature, sufficient oxygen, intact neural networks. It exists for a fraction of a second at a time, updated continuously, and can be disrupted by sleep, drugs, injury, or disease. And yet, within that fragile pattern, entire worlds appear. Pain and joy, fear and curiosity, guilt and love, none of these show up in the equations of cosmology, but they dominate the lived reality of a conscious being. The same universe that is 93 billion light-years across and filled with trillions of galaxies is also the universe in which a single harsh word can haunt someone for years, and an act of kindness can reshape a life. If the self is a pattern, and patterns are emergent, then personal identity becomes less about owning a fixed essence and more about participating in ongoing processes. You are shaped by countless influences: genetic inheritance, family, language, culture, chance encounters, random events. You did not choose your era, planet, or species, yet here you are, thinking thoughts that could not have arisen in any other context. The cosmos provides the raw material and the laws. Life provides the evolutionary history. Society provides the concepts and narratives. The person you experience being is the intersection of all these streams. This perspective can be unsettling. It undermines the feeling of being a detached observer, separate from the world and in complete control. It suggests that much of who you are is contingent and temporary, yet it also offers a kind of liberation. If the self is a process, then it can change. If identity is partly constructed, then it can be reconstructed. The stories told about who you are and what your life means are not dictated by the stars or by the absolute nature of reality. They are created on a tiny, habitable planet by finite beings trying to make sense of their situation. Here is where the implications for daily existence become sharp. Knowing that the universe is vast and ancient does not directly tell you whether to be kind or cruel, ambitious or modest, selfish or generous. Physics is silent on ethics, but the cosmic perspective does alter the context in which those choices are made. The awareness that your life is a fleeting pattern in a universe that will go on without you can provoke despair, or it can deepen appreciation. A moment of laughter with a friend, a quiet walk under the stars, the effort to understand something difficult. These become not trivial distractions from some grand cosmic purpose, but the very substance of what a conscious life is. The realization that perception is an interface can also be a reminder of humility. No one sees reality as it is. Everyone lives inside a model shaped by biology, culture, and experience. Other people's models may differ in important ways. Conflicts often arise when different interfaces collide, when one person's narrative about the world clashes with another's. Recognizing that all these narratives are partial and mediated by limited minds can open space for curiosity, empathy, and dialogue. If even the best scientific theories are approximations, then personal opinions and beliefs are certainly not final truths. At the same time, the work of science shows that shared effort can refine the interface. Instruments extend the senses. Mathematics extends reasoning. Communities of inquiry test, criticize, and improve ideas over time. No single mind can grasp the whole universe, but many minds working together can construct models that capture more and more of its structure. This collective project does not eliminate mystery. It makes the mystery more precise. Instead of, "we don't know anything," the situation becomes, "we know this much, and here is exactly where our understanding breaks down." The impossible galaxies in the early universe, the supermassive black holes that grew too fast, the dark matter and dark energy that dominate cosmic dynamics, the nature of information and consciousness. These are the edges of current knowledge, not dead ends. For an individual life, this has a quiet but profound consequence. You live at a moment when the universe is partially known and mostly unknown. The night sky is no longer a random scattering of lights. It is a map of space and time, a record of how structures emerged from a nearly uniform beginning. You know that the atoms in your body were forged in stars, that your planet orbits an ordinary star in the arm of an ordinary galaxy. You know that countless other galaxies exist, many with their own stars and planets, some of which may host life. You know that the universe is expanding and that far distant galaxies are crossing a horizon beyond which their light will never reach us. You also know that your interface is limited, that your mind constructs a simplified world out of torrents of information, and that your sense of self is a pattern in that world. That knowledge does not change the taste of food or the warmth of sunlight, but it does add depth to them. Eating a meal becomes, in a literal sense, the universe rearranging its own atoms into fuel for a thinking pattern. Standing in sunlight becomes a local interaction with energy that left the sun 8 minutes ago, generated by nuclear reactions that will continue for billions of years. Looking at the stars becomes a dialogue across time, in which ancient light meets a transient observer who briefly understands its significance. In this way, the large scale and the intimate become inseparable. The true scale of the universe is not just a matter of how far space extends or how many galaxies it contains. It is also a matter of how far understanding can reach, how deeply awareness can penetrate its own illusions, and how meaning is created within the tight constraints of a finite life. The cosmos is vast beyond comprehension, governed by laws that are only partially known, built from structures that may be more abstract than matter and more subtle than space. Within that cosmos, a single human life is small. But small does not mean insignificant. A neuron is small compared to a brain, yet it plays its part. A star is small compared to a galaxy, yet it contributes to the galaxy's light. You are one pattern among countless others, a brief arrangement of matter and experience in a universe that will last long after you are gone. You did not ask to be here. You may never know why anything exists at all, but you have been given a chance to see, to question, to feel, and to understand. The same universe that spins galaxies and curves spacetime also made it possible for you to hear your own thoughts, to wonder what is real, and to stand beneath the night sky feeling both tiny and deeply connected. There may never be final answers to the biggest questions. Reality might always remain partly hidden behind the interface of perception and the limits of thought. Yet the act of asking, of reaching beyond what the senses show, is itself a kind of participation in the universe's unfolding. In looking outward and inward at the same time, you become a bridge between the fields and equations on one side and the colors and stories on the other. The cosmos does not explain itself. Through conscious beings, it begins to. The universe keeps its secrets well, even as it offers clues everywhere. Light arrives from the earliest epochs bearing chemical fingerprints of ancient stars. Equations predict the motion of galaxies with stunning accuracy. Instruments probe deeper into space and time, year by year, revealing structures that challenge every previous estimate of how matter organizes itself. Yet beneath all this discovery lies a persistent tension. The closer science looks, the more reality seems to resist simple description. Consider what remains unknown. Dark matter comprises 85% of all matter, shaping the cosmic web, anchoring galaxy clusters, and bending light as it passes through space. It has been detected through gravitational effects in hundreds of independent observations, yet no one knows what it is. Theories propose exotic particles, modifications to gravity, primordial black holes, or topological defects in spacetime. Experiments search for faint interactions in deep underground laboratories. So far, nothing definitive has emerged. The scaffolding holding galaxies together is still invisible, its nature uncertain. Dark energy is even more mysterious. It makes up 68% of the total energy density of the universe and causes cosmic expansion to accelerate. Distant galaxies recede faster and faster, driven apart by something that fills all of space uniformly and does not dilute as the universe grows. The simplest explanation treats dark energy as a cosmological constant, an intrinsic energy of empty space predicted by quantum field theory. But when physicists try to calculate the value of this constant from first principles, they get numbers wrong by factors of 10 to the power of 120. It is one of the most catastrophic mismatches between theory and observation in all of science. Something fundamental is missing from the picture. Then there is the question of what happened before the Big Bang, if before even makes sense. The standard cosmological model traces the universe back to a hot, dense state approximately 13.8 billion years ago, but it does not explain what caused that state or whether time itself had a beginning. Inflationary models propose that the early universe underwent a brief period of exponential expansion, smoothing out irregularities and setting initial conditions. But inflation itself requires explanation. What drove it? What existed beforehand? Some theories suggest an eternal multiverse where inflation never truly ends, spawning bubble universes continually. Others propose cyclic models, where the universe expands, contracts, and rebounds in endless cycles. None of these ideas can be tested directly because events at the beginning lie beyond observational reach. The nature of time itself remains contentious. In relativity, time is woven together with space into a unified structure, space-time, where the distinction between past and future depends on motion and gravity. Quantum mechanics, by contrast, treats time as an external parameter ticking forward uniformly. Reconciling these two frameworks, unifying general relativity with quantum theory, has been the central challenge of theoretical physics for nearly a century. String theory, loop quantum gravity, and other approaches offer partial solutions but lack experimental confirmation. No one has observed quantum effects of gravity or measured space-time at the Planck scale, where quantum properties should dominate. The deepest layer of reality remains inaccessible. Consciousness stands apart as a different kind of mystery, one that touches every other question. If the universe is ultimately patterns of information processed according to mathematical rules, then what is the relationship between those rules and the first-person experience of being? Why does any physical system, no matter how complex, give rise to the sensation of being someone? Neuroscience maps correlations between brain states and mental states, but correlation is not explanation. No current theory predicts which arrangements of matter will produce consciousness and which will not. The question hovers at the boundary between science, philosophy, and something else entirely, perhaps poetry or direct introspection. The discoveries about the universe's scale bring these mysteries into sharper focus. When telescopes reveal that galaxies formed earlier than expected, that black holes grew faster than theory predicts, that structures span distances incompatible with the available time, the implication is clear: the standard model is incomplete. Some ingredient or mechanism is missing. Perhaps star formation worked differently in the early universe. Perhaps dark matter clumps faster under certain conditions. Perhaps feedback from black holes or magnetic fields plays a larger role than currently understood. Each anomaly is an opportunity, a crack in the framework through which something new might be glimpsed. For a conscious observer trying to make sense of existence, these gaps in knowledge can feel disorienting. The universe does not arrive with an instruction manual. It does not explain why it exists or what, if anything, it is for. The desire for ultimate answers runs deep, yet science offers provisional models rather than final truths. Religions and philosophies have historically filled this gap, providing narratives about purpose, origin, and destiny. Modern cosmology neither confirms nor denies those narratives. It simply describes regularities in what is observed, leaving questions of meaning and purpose open. Some find this liberating. If the universe does not impose a single purpose, then individuals and communities are free to create their own. Meaning becomes something made rather than discovered, a project undertaken by conscious beings rather than a fact inscribed in the fabric of space. Acts of kindness, creative work, the pursuit of knowledge, the care of relationships, all become meaningful because people choose to value them, not because the cosmos demands it. In a universe that is mostly empty and mostly indifferent, the small pockets where life and awareness arise become precious precisely because they are rare and fragile. Others find this troubling. The absence of cosmic purpose can feel like abandonment, as if consciousness is an accident that the universe neither notices nor values. The vastness of space and time can make individual lives seem negligible, moments of warmth and effort quickly swallowed by entropy and expansion. If everything known and loved will eventually dissolve, if the stars themselves will burn out, and the galaxies drift beyond communication, then what is the point of any struggle or achievement? These emotional responses are not answers. They are reactions shaped by personality, culture, and experience. Two people can face the same scientific facts and interpret them in opposite ways. One sees freedom and wonder. The other sees isolation and futility. The universe, as described by physics, does not resolve the conflict. It simply is. Vast, old, mostly dark, occasionally brilliant, structured by laws that allow complexity to emerge in particular regions for limited durations. What is clear is that consciousness changes the picture. A universe without observers would still contain galaxies, stars, and planets, but it would contain no questions, no awe, no sense of mystery. Electrons would still orbit nuclei. Photons would still travel through space. Fields would still vibrate according to their equations. But none of it would mean anything, because meaning is something that arises in minds. The universe is not meaningful in itself. It becomes meaningful when part of it, a biological brain, a fleeting pattern of neural activity, reflects on its own existence and asks why. This suggests a deeper relationship between mind and cosmos than either naive realism or strict physicalism acknowledges. The universe produces observers, and observers produce understanding. That understanding feeds back into the universe through technology, communication, and culture. Conscious beings alter their surroundings, send signals across space, encode information in artifacts that outlast individual lives. The James Webb Space Telescope, the images it captures, the theories it tests, all are expressions of the universe's capacity to become self-aware in localized, temporary ways. If you're enjoying this journey into the nature of reality, consider subscribing to our channel, Broken Zach, so you don't miss what comes next. The question then becomes, how does one live with incomplete knowledge, uncertain purpose, and an interface that hides more than it reveals? There is no single answer, but several themes emerge from reflecting on the intersection of cosmology, perception, and consciousness. First, humility. The history of astronomy is a history of discovering that the Earth is not the center, that the Sun is not special, that the galaxy is one among trillions, that the observable universe is only a fraction of what exists. Each step displaced human importance, revealing that the cosmos is far larger and older than any intuition suggested. This pattern should instill caution about claiming final knowledge. Every generation believes it is approaching complete understanding, and every generation is surprised by what comes next. Humility does not mean abandoning inquiry, it means holding theories lightly and remaining open to revision. Second, curiosity. The anomalies and mysteries are not failures, they are invitations. Not knowing what dark matter is means there is still something profound to discover. Not understanding consciousness fully means the relationship between mind and matter is still open terrain. These gaps are where the most interesting work happens, where assumptions are questioned and new frameworks emerge. Curiosity is the engine of science, but it is also a stance toward life, a willingness to look closely, to ask why, to venture beyond comfortable certainties. Third, appreciation. The interface may be limited, but what it shows is extraordinary. Colors, sounds, tastes, the warmth of sunlight, the pattern of stars on a clear night. These are not illusions in the sense of being false. They are real features of conscious experience, shaped by evolution and neural architecture. The fact that a sunset is a perceptual construction does not make it less beautiful. The fact that the night sky is a translation of infrared and ultraviolet into visible hues does not make it less inspiring. Appreciation means valuing experience for what it is, not dismissing it because it does not map directly onto quantum fields. Fourth, connection. The atoms in your body were formed in stars. The photons entering your eyes began their journey millions or billions of years ago. The air you breathe, the water you drink, the carbon that builds your cells all are recycled from ancient processes. You are not separate from the universe. You are a temporary arrangement within it, as much a part of the cosmic story as any galaxy or nebula. Recognizing this can dissolve the sense of isolation that sometimes accompanies modern life. You are small, yes, but you are also connected to everything through chemistry, physics, and history. Fifth, responsibility. If consciousness is rare and fragile, if the conditions that support life are delicate and easily disrupted, then the existence of a planet where complex organisms thrive is not something to take for granted. Earth is one data point in a vast sample space, a place where the right combination of factors, distance from a stable star, presence of water, protective magnetic field, long-term geological stability allowed evolution to proceed for billions of years. Other planets may host life, perhaps even intelligent life, but none have been confirmed. For now, this small world is the only known location where the universe looks at itself and wonders. That knowledge carries weight. Choices about how to treat the biosphere, how to organize societies, how to balance short-term desires against long-term survival all take on cosmic significance. Not because the universe cares, but because conscious beings care, and they have the power to preserve or destroy the conditions that make their existence possible. The interface may hide much, but it cannot hide the consequences of actions. Forests burn, species disappear, climates shift. These are not abstract facts. They are changes that affect the lived experience of billions of conscious creatures, human and otherwise. Finally, creativity. If meaning is not given but made, then the act of creating art, music, stories, theories, relationships, communities is how conscious beings respond to existence. The universe provides the raw materials and the laws. Life provides the capacity to sense and respond. Culture provides the accumulated wisdom and mistakes of previous generations. Each person inherits all of this and adds something new, however small. A single kind word, a solved problem, a moment of beauty shared these ripple outward, influencing other minds, shaping the flow of information through the network of consciousness that spans the planet. The true scale of the universe, then, is not measured only in light years or galaxy counts. It is measured in the distance between what is known and what remains hidden, between the raw physics of fields and particles and the vivid immediacy of lived experience, between the indifference of cosmic processes and the fragile meanings constructed by conscious beings. That scale is overwhelming, but it is also the context in which everything human unfolds. Every conversation, every discovery, every fear and hope happens inside this vast, ancient, mostly empty expanse that briefly gives rise to minds capable of asking what it all is. No conclusion can tie these threads together neatly because they do not resolve. The universe continues expanding. Galaxies drift farther apart, stars form and die. Black holes evaporate over unimaginable timescales. Entropy increases, smoothing out structures, erasing complexity. Eventually, if current models hold, the cosmos will grow cold and dark, with isolated remnants of matter scattered across distances so vast that no signal will ever cross them. The night sky will go black. No new stars will ignite. Consciousness, if it persists that long, will fade along with everything else. But that ending lies trillions of years in the future. Right now, the universe is young. Stars still burn, galaxies still collide and merge, planets still orbit in habitable zones. Life still evolves, learns, and adapts. Consciousness still arises in nervous systems scattered across at least one world, and perhaps many more. The interface still translates raw physics into colors, sounds, and stories. The mysteries remain open. You are here now, able to think these thoughts, to feel the weight of these questions, to stand in the lineage of countless beings who looked up and wondered. The universe that made you also made the stars, the telescopes, the equations, and the capacity to care about what any of it means. That capacity is rare. It may be fragile. It is certainly temporary. But while it lasts, it transforms part of the cosmos from mute existence into something aware, something that asks, something that marvels. The James Webb Space Telescope revealed that the universe is larger, older, and stranger than previous instruments suggested. It found galaxies that should not exist, black holes that grew too fast, structures that formed too early. These discoveries do not diminish the cosmos, they expand it. They remind every observer that the interface is always incomplete, that the map is never the territory, and that the search for understanding is never finished. What seems impossible today may be routine knowledge tomorrow. What seems final may be overturned by the next generation. In the meantime, there is this: a small planet, a single species capable of asking why, a night sky filled with ancient light, and the quiet, persistent effort to see a little farther, understand a little more, and find meaning in the brief interval between birth and dissolution. The universe does not need you to understand it, but you are here and you can try. That effort is its own kind of answer, not to the question of what reality is, but to the question of what it means to be a conscious part of it. The true scale of the universe is not a number. It is the relationship between the immensity of what exists and the narrow aperture of awareness through which it is glimpsed. It is the gap between the equations and the experience, between the cosmic indifference and the personal significance. It is the recognition that you are both insignificant and irreplaceable, a speck in space-time, and also the only place in your corner of the cosmos where the universe knows itself. That paradox cannot be resolved, only lived, and perhaps that is enough. If you enjoyed this video, watch this one too. It's a great one, and we'll see you in the next video.